Kinematics 21, resultant motion and relative motion. A sort of this I have talked about in vectors, but we'll be doing it in more details now. See, the heading is the resultant motion and relative motion. Even this will be motion in a plane we'll be discussing, or motion in a two-dimensional plane. Here we need to use the idea of reference frame liberally. Okay, in the beginning it looks a little difficult to get used to it, but if you're open-minded, you'll get used to it and you'll appreciate it, you will like it. Okay, but once again you need to keep speaking. What is this resultant motion or relative motion? I'll give you a simple example. I'll start with an example here. Most simplest of the things to understand. Say there is a carriage moving like this with 10 meters per second. There is a person standing on the ground. Standing. This is observer A. There is an observer B inside the carriage. B, he is also standing inside it. I should write standing inside. Now, both of them watch one person C moving like this. This person C is moving with, say, 0.5 meters per second. So for the person B, the C appears to move with 0.5, but for A, the velocity of person C is 10.5. I'm using certain words which are used in the popular usage. I have not yet used the word reference frame. I might say like this: C is moving with 0.5 meters per second is the feeling of person B, but actually C is moving with 10.5, I'll say, which looks all right to begin with, but not a good idea. Look, motion and rest are relative terms. Motion and rest have meaning only with respect to the reference frame in which you see that event of motion or rest. And remember, people use words like actually, feeling, without much thought. I'll tell you something. Now you're sitting in your chair and watching, looking at the screen and listening to me. Somebody nearby you is also sitting on the cot or a chair there. You look at them, you'll say they are at rest. But remember, for somebody watching from somewhere, from moon, for example, you both are in motion along with the earth. When you sit inside a plane, an aeroplane, your fellow passengers are all sitting and at rest with respect to you. But all of you are moving with respect to somebody standing on the ground. So you need to understand that motion and rest are always relative words. They don't have a unique meaning. They don't have an absolute meaning. They have a meaning only with respect to the surroundings in which you watch them. But the word surroundings is a very broad one, loose one. We need to put that in terms of a reference frame. And reference frame is nothing special. A reference frame will be all the time fixed to one body, one rigid body, one body whose dimensions are not changing. So for example, here we'll say that the speed of the carriage, or I can call it a box car. I'll say that the speed of the box car in a reference frame fixed to ground is 10 meters per second. The velocity of the box car in a reference frame fixed to the ground is 10 meters per second. Here ground is the rigid body, and this x, y, z is the coordinate system fixed to that reference frame, fixed to that body. So here ground plus x, y, z coordinate system put together you can call a reference frame, and you stand at the origin of the reference frame here and watch this car moving with 10 meters per second. Do you follow? But a person standing inside B, for B, car will be at rest. Isn't it so? Tell me. You can think has no information of what is happening outside, in the sense the curtains were drawn, he's not allowed to see outside. The moment B sees outside, since the trees and buildings will be falling behind him, he will know that the boxcar is moving. Otherwise, for B, inside when he sits, the boxcar will be not moving. So who is right? Don't say A is right and B is not right. A is right, B is right. In the reference frame fixed to the car, you can say it is x dash, y dash, like that, and you can also put z dash if you take the width of the boxcar. So that now you can say in a reference frame fix the car, which is x dash, y dash, z dash, the bus is at rest, or the car is at rest. So now look at this. The person B here says C is going with 0.5. This 0.5 is what? Velocity of C relative to the car. Do you follow? Hello?
Yes, sir.
And velocity of, this is velocity of C I put, right? This, okay. Velocity of boxcar with respect to ground is how much?
10 meters per second.
10 meters per second. Now, velocity of C with respect to ground will be velocity of boxcar, or let me write velocity of C with respect to car plus velocity of boxcar
with respect to ground.
That is 2, so not 2, this is 0.5.
0.5 plus 10.
10. This is 10.5 meters per second. Now, this can be, of course, here this 10 meters per second and 0.5 meters per second are in the same direction, right? So we say that C is moving with 10.5 forward. Why? The car moves forward, and within the car C moves forward. Do you follow that? Hello?
Yes, sir.
But supposing C was going in the opposite direction with the same 10.5. So in which case, velocity of C with respect to ground observer will be, tell me, 10 minus 0.5, 9.5 meters per second forward direction, right?
Yes, sir.
Right. So you should never say it is only sum of these two velocity speeds. It can be some difference Or say, for example, he is going along the width of the car with 0.5 and car is going like that with 10. This angle is 90 degrees, you think. So for a person on the ground, he will be moving like that with 10 square plus 0.5 square under root. Hope you followed. Velocity of c with respect to ground. You know, this 0.5 is which way? Into the depth of the car, like this, perpendicular to it. He is walking from this window to that window. With respect to B only says this fellow is walking like this. And A will say, no, he's not walking like that, he's walking like this. With 10 square plus 0.5 square under root. Now this motion, velocity of C with respect to ground, will be called the resultant motion. And in general, we'll write it as a vector sum. Here we added, here we subtracted, here we put the Pythagoras theorem, isn't it? So in general, we'll be using cosine rule. You understand my point? So velocity of an object with respect to what? A reference frame, or in a reference frame is the most appropriate, fixed to ground or lab to make it more scientific. To fix the ground is, or not velocity, motion of an object with respect to a reference frame fixed to ground or lab is called resultant motion. So I'll stop here for a while. I want you people to speak. You need to really get that intuitive understanding of the things here. Once you do that, we'll make it mathematical, we'll make it analytical, we'll make it algebraical. So in general, this can be written as, this velocity business can be written as velocity of an object with respect to a fixed frame, that is ground frame in this case, is equal to velocity of the object relative to the moving frame plus velocity of moving frame with respect to fixed frame. Vector sum. Remember, when we say vector sum, it includes all cases. The angle between these two velocities will be between 0 and 180. All cases will be taken care. Now, this is the theta equals 0 case, this theta equals 180 case, this is the theta equals 90 case. Not only 3 cases, but we can include many more cases from 0 to 180. And remember, all the time the angle between two vectors can be between 0 and 180, including 0 and 180. Now tell me, Phyllis.
Yes, sir.
So are you okay with these words? In a reference frame fixed to ground, in a reference frame fixed to the boxcar, or with respect to ground, with respect to boxcar. This is the kind of wording we need to get used to.
Yes, sir.
If this is okay, we can make it more mathematical. I'm dealing with the word resultant motion for a while. I need not have to use this word, but what happens is in the textbooks, in the guidebooks, everywhere, this kind of headings are given. So any questions, children? I want you to write. Rakshil.
Yes, sir.
I want you to write. I've given a very simple example. What is 10 meters per second, Rakshil? What is 10 meters per second?
The speed in which the bus is moving.
Huh?
The speed in which the bus is moving.
That is, the bus is moving with respect to whom?
With respect to A.
With respect to A. Remember, there's nothing like velocity of bus. When you say velocity of bus, you should say with respect to whom. Only then the velocity has a meaning. Do you follow? Huh?
Yes, sir.
If you are sitting in the bus, can you say 10 meters per second the velocity of the bus?
No, sir.
What will you say is the velocity of the bus when you sit in the bus?
It
Zero.
would be 0.
The bus will not be moving with respect to him. Is that all right?
Yes, sir.
Is that all right for others? Amar. Don't say, how can that be 0 for somebody and nothing for somebody? Remember it. Velocity or rest, motion or relative terms. It is not just physics. It is a practical feeling, children. You need to understand. If you ever travel in an aeroplane, you will know that. The aeroplane may be going with a very high speed actually for a person standing on the ground, but you will not feel that you are in motion unless you look through the small windows and clouds pass by, or even if there is some kind of a turbulence happening in the air, you don't even know that the plane is moving. See, there's a thing called hyperloop. Tube trains, they'll be going even with higher velocities.
Yes, sir.
But when you sit inside, nothing. It doesn't appear to be moving at all. So that should tell you that motion and the rest are only, they have a meaning only with respect to the reference frame in which you see them. So if I said for B, the bus is not moving, are you going to be worried?
No, sir.
You should not. Huh? Right. And what is 0.5 meters per second?
So velocity of person C with respect to person B.
Yeah. So every time, remember, we are not studying A and B. We are studying whom? C. We are applying physics for C. So there will be always a person to whom we apply equations, or a body to whom we apply equations. And there will be many persons applying these equations from different reference frames. So don't worry about the force on B. Don't worry about the force on A, motion of A, motion of B, all that you need not worry. I mean, we'll talk about that slowly, but right now you need to understand that C is the one to be studied. C is being studied by B and as well A. So for B only can say that C is going with 0.5 meters per second. That means in 1 second he'll cover half a meter. That's all. Right? But for him, C will cover 10.5 meters in 1 second. Isn't it so simple? Like the bus will not be here, isn't it? For A, bus will be somewhere there and the person is somewhere later. Do you follow? I'll just show it. Look at this. Say this is the observer B. Observer is here, C. This is the situation now. And of course, there is our person A also. Okay. After some time, what happened, you can give some name, some numbers if you want, but let me see. After some time, if I draw one more figure, the bus is here. This was, say, for example, 1 meter now, but now this is 1 meter. This is also 1 meter, you think? Huh? Hello, do you follow? Now, this is B. C is at 1.5 meters from him. Hello. And say the bus's speed is 2 meters per second. Hello. Bus's speed is 2 meters per second. Initially, this end of the bus was at 1 meter. In 1 second, this will become how much? 3 meters.
3 meters.
Do you follow?
Yes, sir.
Hello. So with respect to him, he moved 0.5 in 1 second. Who? C. With respect to A, he moved how much?
4.5 meters.
4.5. Did he move 4.5? No. The bus was initially here. This was the position of the bus. I'm telling you, this person's velocity is 0.5 meters per second. Do you follow? Now tell me. Hello. This is 2. Come on.
He moved 2.5 meters.
0.5 meters per second. Isn't it? Hello, children.
Yes, sir.
Of course, the figure was not very correct. Doesn't matter. So, who is right? You will say A is right or B is right. Both are right. For B, he will move 0.5 extra. For A, he will move 2.5 extra. Do you follow? So, for him, this is correct. For him, this is correct. Do you follow? So, you should not. You should never feel that. Of course, if just the numbers you set properly here. I don't want to rub it off and write. So we will never say that something is actual, something is feeling, something is real, something is not real. What is actual? You never ask in physics as far as velocities are concerned. Do you follow?
Yes, sir.
So what are we doing? Why are we calling it resultant motion? Do you know? It became a habit because you are writing one velocity, the sum of two velocities, as the vector sum of two velocities, basically. As the vector sum of two velocities, you are calling it resultant velocity or resultant motion. Don't we know? Like if there's a vector A here, if there's a vector B here, you say this is R, which is R equals vector A plus vector B. We call it resultant of A and B, right? Hello.
Yes, sir.
Yes, sir.
So that's the reason we use the word resultant motion. So if you ask me in words, what is resultant motion? I can just tell you something in words, though, which is not very, very important. Look, the motion of a body in a fixed frame. Fixed frame means here what, children? A reference frame fixed to ground or lap in a fixed frame is the resultant of, tell me, resultant of the motion of the body relative to the moving frame, and motion of the moving frame with respect to the fixed frame. So the English has to be understood. Instead of saying in a fixed frame, you can say with respect, if you feel comfortable with that. The motion of body with respect to a fixed frame is the resultant of the motion of the body relative to the moving frame and motion of the moving frame with respect to the fixed frame. If you can repeat this in your mind, I can say that you understood it. But in physics, English words or Telugu words or Hindi words are not important. Ultimately, the language of physics is maths. How to show this thing in mathematical terms, I'll show you now. Are you ready?
Minutes, sir.
Right. Look at it. But this is a little vector way and analytical way. Just look at it carefully. This is a reference frame fixed to ground. What am I saying? Reference frame fixed to ground is a general wording we use in our intermediate classes. A proper word will be a reference frame fixed to lab. That means wherever you are, even if you're doing it an experiment on the landscape there, that is your lab basically. But labs will be fixed to ground, earth. Okay, but doesn't matter. Reference frame fixed to ground. Once again, I am telling you, reference frame is not, don't say it is in the mind, it is actually a very physical one. Say for example, this is my iPad and there's an ant moving on my iPad. So there will be a person standing here and watching the ant. So we'll say that in a reference frame fixed to the iPad, the ant is moving with the ant is moving with 1 meter per second. But the iPad is also moving, for example. The ant won't be knowing the iPad is moving. Try to understand. So we'll fix a reference frame to the table here. So a reference frame fixed to table, a reference frame fixed to the iPad, I am saying. That means anytime reference frames are fixed to what? Some bodies. Remember it. There's nothing else that reference frame will be fixed to, fixed in space like that. So one body where you stand upon and watch another body's motion is called a reference frame body, basically. That is why I'm saying reference frame body means there are two bodies, one body to be observed, another body on which I stand and watch this. So there's a body for the reference frame, but just reference frame is not the body itself. You fix one X, Y, Z coordinate system to it and have your measurements there. For measuring, you have watches. For measuring lengths, you've got scales or rulers. All that arrangement is what you call reference frame. Hello, do you follow?
Yes, sir.
Reference frame fixed to ground, reference frame fixed to the water, reference frame fixed to the train, reference frame fixed to the plane, reference frame fixed to moon, reference frame fixed to the fixed stars, like that. Every time there should be a material body on which an observer is supposed to be rigidly fixed himself or herself and watch events happening out there. Okay, that's the reference frame fixed to ground. And there is one more reference frame, moving reference frame. I do not have to mention the body here. There is a moving frame. Moving frame is, this is moving with respect to the what?
Fixed frame.
Fixed frame, that's correct. So you can give a coordinate, position coordinate for that. This origin of that reference frame, we can call it S frame. This has S dash frame. Hello, this is the Z axis. Okay, here X, Y, Z or Z. This X dash, Y dash, Z dash. So this position vector shown with the red arrow will be called R of the moving frame with reference to fixed frame. I write MF stands for moving frame, FF stands for fixed frame. Now there is a body to be studied. This is our person walking inside the bus. See, you know, this is my observer B in this frame, observer A in this first frame, fixed frame. But I am watching this C here, like we discussed in the previous example. His position as measured from the fixed frame is R FF, right? But this body is also watched from, tell me, the moving frame. This is R of the body relative to the moving frame. So generally I use the word R relative. That's enough. So relative is relative position, relative velocity, relative something is all the time velocity of some body with respect to another body which is moving with respect to ground. So from the law of triangle of vectors, from the law of triangle of vectors, what can I write? Could you tell me? R of moving frame with respect to fixed frame plus R relative is equal to R FF. Do you agree?
Yes.
Hello?
Sir.
Yes, sir.
Phyllis,
Yes, sir.
Nihita,
Yes, sir.
Enoch, R of this moving frame plus R of the body relative to the moving frame is equal to R of the body with respect to the ground frame. Is it okay? Remember, this will keep coming again and again and again in my lessons. Throughout the 2 years of physics, this will keep coming. This is putting things on the firm theoretical basis. First of all, you need to understand that there will be many problems based on this. River problems. River problems means not the river problems between Telangana, Andhra, or between Tamil Nadu and Andhra, or between Karnataka and Telangana. River and boat problems, people say. Aeroplane and wind problems, people say. Bus and person moving. Like that, they go on giving names like this to problems. And try to remember every case as if it is different. But what you need to understand is that so many differently looking problems, different physical situations rather, they are different physical situations. There is one basic behind. That is what you mean by the concept basics or fundamentals or whatever. So this particular small thing will keep coming again and again. What is it? The position of a body. This RFF, what, children? Position only, isn't it? Position vector or position, to make it look short. Position of a body with respect to ground, like position of that person in the old example. Position of what? C with respect to ground is the vector sum of the position of the person C with respect to B and position of B with respect to A. Hello, isn't it? So it's very visible. Like if this is 1 meter, and if this is 1 meter, 1 plus 1 is 2 meters of C with respect to A, isn't it? Hello.
Yes, sir.
So I want you to keep giving the feedback when I especially demand you something. Because I'll tell you, after all this kind of what you say, telling things again and again to you people, many times students and parents come to me, half an hour I'll speak, they'll say, sir, what is the technique of doing things? People ask me. Sometimes if I'm in a good mood, I'll laugh. Sometimes if I'm not in a good mood, I'll hit my head. Remember, there are no tricks. people make it look like tricks. The tricks are there already in physics. The trick is this. What is the trick? VFF equals VL2 plus V, this one. This trick applies to many problems. Isn't that a trick? So my
Yes, sir.
expectation from you people is this. You should really listen to me carefully and keep asking. Then things, if they don't work out, you ask. So, yes. Now, we're not giving any example here. We took one example. I could have given you many more. But anyway, since we are going to do all those examples later, I have not exhausted them in the beginning itself. 10 different examples are connected to only one idea. What is that idea? I've shown it vectorially here. Position of the body with respect to the ground frame is the vector sum of position of the body relative to the moving frame plus position of the moving frame with respect to the ground frame. You can write this first if you want. Here say RFF, position of the body with respect to ground frame or fixed frame is position of the body relative to the moving frame plus position of the moving frame with respect to fixed frame. For rhyming case, say you can write this first. Why am I saying rhyming? Position of the body. Basically, we are interested in position of the body, not in the position of the moving frame. So position of the body in the fixed frame is equal to position of the body relative to the moving frame plus position of moving frame with respect to fixed frame. So this what do you call word play, if you really understand. See, it is there. Mathematics is there for you to see, right? What do you say? Now, for example, differentiate this with respect to time. Differentiate with respect to time. What will I get? Velocity of a body. Shall I write straight away? dRF by dt, should I write? I'm saying that in words, I need not.
Yes.
Hello.
Yes.
Differentiate, that is dRFF by dt is equal to dr relative by dt plus dr of the moving frame with respect to fixed frame by dt. So this gives what? Velocity of the body in the fixed frame is velocity of the body relative to the moving frame plus velocity of moving frame with respect to fixed frame. This is what we written down straight away there because that was okay with the for the examples. But the main thing starts from relating positions. Do you follow? You spend enough time on this, I'm telling you. Don't say this I understand, but I cannot apply for problems is absolutely meaningless. Do you know? Unless you enjoy being in your comfort zone. Now, what follows after this? Can I go to the next slide? Children.
Yes, sir.
That's it.
Be sure that you're understanding it. Speak or just confirm that you understood. Say you take my permission and explain it to others. Come on, see, boys and girls. This is something like this. This is something like this. I think, I mean, you can actually elaborate it. I know students who are putting everything in their own way, in their own words. Sir, this is what I understood. Please tell me whether I'm right or wrong. People keep asking. Now, just this particular thing. Remember, like this, there are some around 30 plus ideas like this. The total thing is physics. That's all physics. That's all there in physics. Rest is all simple manipulation, solving linear equations, solving quadratic equations, and knowing some differentiation integration. That's all. Otherwise, the physics ideas are around just 30 in the 2-year syllabus, believe me. Or 30, a little more than that. If you subdivide, you may get 40. 40 are the ideas, but see, ideas, big ideas, grand ideas. Grand ideas are already, there may be some 6 to 7, but 30 main ideas have, or physics has. So you need not have to bother about the syllabus and feedback exam, all that. It will come. People are worried. Come on, where is the exam? Where is the test? The kind of test I put, you will flop. So what is the point? I should make you ready for a good test. So can I continue? Amar? Amar? Willing to speak? Many people did not come again. So what people are doing at home, we don't know. They blame it on the online classes later. Your mic is not working. So can you give me permission to change this? Don't sit like that.
Yes, sir.
Yes, sir.
Yes,
This is once again a problem. Like people sit like this. If I sit like this, they'll sit like that. So nobody will be ready. Come on, why should I say? Somebody else will say something. If you finished it, say you finished it. If somebody has a problem, he'll ask me to not to change. So these fellows have already. I'm going out. I don't know why. Now, if I differentiate this again with respect to time, I'll finish it here itself so that I don't miss the other things there. Position here, velocity here. Differentiate this. Can I write A of the body with respect to fixed frame is equal to A relative plus A of the moving frame with respect to fixed frame?
Yes, sir.
By differentiating again.
Yes, sir.
Sir.
Tell me. And I'll show you something very important here. If you did not follow, don't worry, but that will come in future. Shall I go to the next page? Hello.
Yeah.
Yes.
Look, A of the body from ground frame, fixed frame, whatever you would like to say, is equal to A of the body with respect to the moving frame, which we call as A relative, plus A of the moving frame or moving body with respect to the fixed frame. Okay. Suppose the moving frame or the body, moving body, let me say, to which a reference frame will be fixed. Moving frame is going with a constant velocity. With a constant velocity. What is the implication of that? What is the implication of that? Come on,
The
I'll wait.
acceleration is 0.
Which one is 0?
The acceleration.
Which one? The first term or second term?
Second one.
Second term, right. So A of the moving frame with respect to fixed frame is equal to 0, which implies A of the body in the ground frame is same as A of the body in the moving frame. Can you tell me what does it mean? Can you tell me what is the meaning? The whole this thing. Look. I have a lift, I'll tell you. An example, I'll tell you. Remember, try to understand the ideas. I don't want to use the word concept because nowadays the word concept is really scary. In the textbooks, the problem if there is a concept means he writes something there, like some formula he writes, sometimes something they write. Ultimately, what is not problem, but what you speak is concept, something like that. Remember, concept can never be so silly like that. Here I'll give the example, and the concept you need not have to put it in words, understand it, feel it, that's all. I have a lift. This lift is going up with an acceleration of A equals 2 meters per second square, I'll say. But immediately you should ask me, sir, with respect to whom is this acceleration? With respect to whom?
Ground frame.
Yes. You are watching the lift standing on the ground there. So you will say that lift is going with 2 meters per second square. Okay. Now there was one bulb to the floor of the roof of the lift. Somehow it got detached. The screw got detached. So the bulb will fall. Right? Hello.
Yes, sir.
The bulb is falling. I'll say got detached. What is the acceleration of the bulb? Ignore air. So tell me, Vasist, with what acceleration the bulb falling to the person A to a person B? A is fixed rigidly to this ground, B is fixed rigidly to the lift.
Yes, sir. So for A, it's just falling with G, but for B, it's falling with G plus 2.
G plus 2, that's correct. So he's very clear now for that. With that, others tell me. For A, the bulb is falling with 10 G, but for B, this falling with 12. Do you all agree? And how do you put it in our mathematical terms? Look, A of the bulb so do you follow this? From here it comes A of the bulb with respect to floor A of the bulb with respect to floor, that is outside, is A of the bulb relative to the lift plus A of the lift with respect to floor. Vector sum. Do you follow the meaning of this statement, children? A of the bulb with respect to floor, that is here. A of the bulb relative to the lift. Now relative to the lift, how much? Here, of course, I should write A relative for him actually. This is A relative to the floor. Lift is equal to A of the bulb, because we know A of the bulb with respect to ground. A of the bulb with respect to floor minus A of the lift with respect to floor. So the vector now A of the bulb with respect to B will be vector difference of G and A. G is up, G is down, A is up. So the resultant is how much? G plus A. When the angle is 180 degrees between two vectors, A minus B mod equals mod A plus mod B. If theta is 180, cosine rule. Or in a simple way, I told you many times, let this B reverse his own acceleration, A, and add it to it. So G plus A down, that way you can easily understand it. Are you listening? Hello, from here I am writing bulb's acceleration with respect to the lift. From this relation, I have took it this side and took it this side. So the vector difference of G and A. G is down, A is up. So vector difference will become what? G plus A down. I don't know whether people have remembered anything like this. Hello. But now let me say one more example where the lift is going up with a constant V. Now the bulb is dropped. So for him, this comes down with G. For this fellow also, it comes down with G. V constant. Tell me whether you understood this statement. The bulb is going with a constant velocity.
Yes, sir.
Hello. The bulb will be falling down with G for B and also for A. What do you say?
Yes, sir.
So this is actually Galileo's principle of relativity. This is, which I'm not giving a name to it right now. People get frightened. So this is based on the main idea of Galileo's relativity. Hello. Write it anyway. I'll stop it here. Actually, in the timetable, my class is given tomorrow. I forgot to tell sir, but tomorrow and day after tomorrow I'll be busy. Even today I was busy, but you are hearing certain songs and sounds. So I thought, let me finish anyway class today, but this class won't be there tomorrow and day after tomorrow. Do you follow? 17th and 18th, 19th we'll meet again. All right. Hello.
Yes, sir.
Yes, sir.
Okay then.
Thank you, sir.
Thank you, sir.
Close it.
Thank you, sir.
Thank you, sir.
Thank you, sir.